Good morning. My name is Erol Sancaktar. I am professor at the University of Akron, Department of Polymer Engineering. Today, I would like to talk to you about Excimer laser treatment of steel fibers for improved adhesion to silicone rubber. I would like to acknowledge my coworker, Dr. Xiaoxiao Liu. Former investigators observed characteristic laser-induced structure on synthetic fibers and steel core surfaces after irradiation. This is considered an advantageous factor in developing bonding strength of fiber-elastomer composites. Thus, we applied various UV laser treatments on the surfaces of laser fiber in order to obtain similar topographic features. We make a conjecture that such laser-induced structures on fibers providing higher surface roughness may improve fibers' adhesion to silicone rubber, and the gaps between these roll-like structures provide more approachable space for the relatively soft matrix material. Thus, additional gripping force applied on the fibers from rubber contributes to the adhesion of fibers to the matrix. A theoretical prediction of increase in bonding strength of fiber-rubber composites could be acceptable if showing a reasonable agreement with fiber pull-out test results. And our experimental results revealed better adhesion strength when using a silicone rubber matrix reinforced with carbon black. Our goals involved applying various UV laser treatment on surfaces of steel fiber in order to increase bonding strength of fiber-elastomer composite by inducing topographic features. For example, on upper right here, I show Excimer laser-treated titanium surface which acquires rippled wave-like surfaces. We then would like to observe the induced surface modifications by microscopy. And we want to perform fiber pull-out adhesion strength tests using the method developed by our research group for determining bonding strength of carbon fibers to silicone rubber in both neat and carbon black filled forms for comparison purposes. We used 248 nanometer wavelength krypton fluoride excimer laser in the past to ablate aluminum surfaces, which were subsequently bonded with an epoxy adhesive. The topography of each irradiated area consists of quasi-regularly spaced waves that advance towards the peripheries, which were about 5 micron above the non-irradiated metal. And this was obtained when we used 20 pulses. We then made symmetric single-lap shear joints from treated coupons and observed considerably increased strains at fracture and about 24% greater joint strength as compared with controls. We also performed another project where we again looked at aluminum and titanium surfaces. We used pulse numbers varying between 20 and 1,000 pulses applied at 250 millijoules energy level. The ultimate strength for the irradiated aluminum substrate joints were 15% greater than the controls, and the strain at fracture for the irradiated joints were about 60% greater. With titanium, no significant effect was observed for the stress and deformation values, perhaps due to the stiffer, harder nature of titanium. But we did observe a reduction in the shear modulus from 51.7 megapascal down to 30.7 megapascal when we used 20 pulses, which indicated a softening behavior. There are other studies available in the literature. For example, researchers observed similar wavy surfaces when they irradiated copper-coated steel cord surfaces. We have performed a nonlinear viscoelastic modeling of the fiber matrix interface by using numerical analysis, and showed that increases in interface thickness reduce fiber and stress concentrations. Similarly, softening of the interface, reduction in this modulus, also helped reduce stress concentrations. Another issue that we pay attention to is to make sure that the wavelength that we use is adequately absorbed into the substrate. And in this case, 248 nanometer wavelength we use is appropriately absorbed by the steel cord. The steel cords we used were obtained from Bekaert company in Belgium. This cord is spirally, helically wound multi-layer cord, as shown in the middle pictures here. And the properties of the cord are also shown on the upper right. One point to emphasize is that the cores that we obtained had a brass layer coated with a thickness of 0.2 microns. And to see the efficacy of the irradiation, we had to remove this brass layer by using aqueous ammonia solution in the presence of oxygen. And the removal process chemically can be seen by this chemical reaction in the middle of the slide. The polydimethyl siloxane PDMS material, commonly called silicone rubber, is the matrix that we used. It's a viscoelastic polymer, but it becomes elastomer after curing. And that's why it's commonly used for substrate bonding. We obtained this material from Dow Corning in two-parts kit containing base and the curing agent, where they were mixed 10:1 proportions, 10 base to 1 curing agent. We then embedded a single steel cord with an embedded length of 10 millimeters into this material that was cured. And we also added in the matrix carbon black, as I mentioned, carbon black of 22 nanometer size in 10% proportion for reinforcement purpose. The Excimer laser we used is 248 nanometer krypton gas laser. We applied it in open air, so it does cause oxidation, which is considered by some researchers as an advantageous layer for adhesion. We irradiated the cords using 50 and 1500 pulses, and the fluence was varied between 500 to 1500. The repetition rate was kept constant at 1 Hertz to avoid heat accumulation. And we used optical microscope to observe the surface features. The 10% carbon black PDMS blends were mechanically stirred for 24 hours, and then the curing agent was added. After manually stirring for 10 minutes, the mixture was degassed under vacuum for 30 minutes. The carbon black PDMS rubber was cured in an oven at 60 degrees for 8 hours, and no pressure. We used the ASTM D4776H test method as the pull-out test for the measurement of adhesion. The specimens were prepared by using the molds that we machine in-house. The molds are shown on the right-hand side here. The cavities are filled with the compound, and the cord is laid over these two cavities. One side has the embedded length, and the other side, the cord goes through that rectangular section. And the resulting cured specimen is shown on the upper right. You can see the rectangular matrix coupons, each of which are 50 millimeter in length. And this is gripped on both sides in the grips of the instrument testing machine, and the fiber pulled out. The pull-out condition is modeled by using the classical equilibrium condition, where the interfacial shear stress tau in this equation on the bottom represents the adhesion strength. Le is the embedded length. R is the radius of the fiber or the cord. And sigma is the stress that develops in the fiber by the force F, which is the pull-out force which we measure. The results of our experiments are shown on this slide. On the upper left, we see an optical microscopy photograph of the irradiated area. We can see the ripple structure created when we applied the 248 nanometer laser using 1,000 pulses at 1,000 millijoule per square centimeter fluence. Increasing number of laser pulses and increasing laser fluence expanded the distance between the hills, resulting in coarser structure where the previous hills joined by melting and the gaps occupied larger spaces. The table on the lower left shows the effect of adding carbon black in 10% proportion. You can see that both the shore A hardness and the storage modulus G prime at room temperature both increase when we add the carbon black reinforcement. The table on the right shows the increase in adhesion when we do the pull-out test. The lower part is with the carbon black PDMS cord composite, which gave us well-behaved results. You can clearly see when we go from 500 pulses to 1,000 pulses, the adhesion goes from about 18 newtons pull-out force to about almost 25 Newton pull-out force. So there's a clear increase in the adhesion, and the same thing occurs with the increase in fluence. The results with the neat resin PDMS cord composite was not as well behaved, as shown on the upper part of the table, even though we still see some increase in adhesion when we increase the number of pulses and fluence. In conclusion, we can say that laser-induced region on surface of steel cord reveals wavy structures. The mean surface structure distance of steel cord is governed by laser fluence and the number of laser pulses. By increasing the laser fluence or number of laser pulses, there is a clear development of structure distance. Structure melt and solidification within induced region results from the thermal concentration, which is governed by the laser fluence. When we did the pull-out test, we did not see any matrix fragments on the cord that was pulled out, indicating that the failures were interfacial. The characteristic high flexibility of silicone rubber obviously adds to its wetting of these surface features that we create. However, with low modulus neat resin, a large deformation difference exists at the bonding interface with embedded fiber, facilitating debonding. An increase in bonding strength is observed under the same irradiation condition on steel cords embedded in carbon black reinforced matrix resin as attributed to increased matrix modulus. So when we use the silicone rubber, any increase in adhesion strength to embedded fiber is also attributed to the characteristic laser structures obtained by laser irradiation. Irradiation using the same laser fluence with more ablation pulses, creating hill and valley structure occupying large gap spacing, resulted in higher adhesion strength in comparison to less laser pulses. Thank you very much for your attention.